Welcome to How the Heavens Go. I'm your host, Mark Lesmeister. Last time we looked at some early models of celestial motion. We saw how models such as that proposed by Aristarchus, where a stationary sun was orbited by a moving Earth, could explain the apparent motions of the sun as seen from Earth. Today we're going to examine some objections to those heliocentric models, and we're going to see what the alternative was proposed by the ancient Greeks. But first, let's take a look at what happened to our model when we added bag 3. Bag 3 adds a rotating arm to the structure, which is going to give us the orbital motion. We also get a large yellow sphere in the middle, which, as Brian Reagan reminds us,
the big yellow one is the sun.
Thanks, Brian. However, models with the big yellow one stationary in the middle and a moving Earth presented some difficulties. One is that it doesn't feel as if the Earth is moving. We are used to feeling circular motion. If we were to drive around a 100-meter wide circular track at 30 miles per hour, we would feel it. But we don't really feel constant motion. What we feel is changes to motion. And on a planet that is moving in an orbit that is 300 million kilometers wide, doing one revolution per year, although we are moving very fast, our motion is changing very slowly. Another objection ancient astronomers made with heliocentric systems was that if the Earth is moving, the direction to a distant object, such as one of the fixed stars, should appear to shift. This is called parallax. Let's illustrate how parallax works in astronomy with the model. Let's say we want to know how the angle between the direction to the constellation Cat Dog and the constellation Cup changes during the course of a year. Today I've placed Cat Dog in the direction of the sun as seen from the Earth at the equinox. At the spring equinox, the angle between the direction of Cat Dog and the Cup constellation is about 60 degrees. 6 months later, when the Earth is on the opposite side of its orbit, the angle between the direction of Cat Dog and the Cup constellation is about 123 degrees. However, no such shift in the angles between constellations is observed in the real world. Aristarchus was well aware of the problem posed by this lack of stellar parallax. That is the reason Aristarchus placed the fixed stars at a large distance from the other planets. The farther away the fixed star constellations are, the smaller the observed parallax. The original documents in which Aristarchus described his heliocentric system have been lost, but there are references to his system in the works of Archimedes of Syracuse, the famous inventor, philosopher, and solar-powered heat ray designer. Using Archimedes' calculations, translated into modern terms, Aristarchus may have placed the fixed stars about 2 light years away from the Earth. That's about 1/2 of the real distance to the nearest star, Alpha Centauri. Astronomers did not have the tools to detect the minute parallax shifts such an enormous distance would entail until the 19th century. Perhaps most thinkers in the ancient world were not ready to expand the universe in the way that a moving Earth would require. So the model that prevailed was the geocentric model, which put a non-moving Earth at the center of the cosmos. With a non-moving Earth, the angle between the moving fixed star constellations would remain constant as they rotated about the Earth. The extremely influential philosopher Aristotle, building on the work of Eudoxus, proposed a geocentric cosmos consisting of nested spheres. At the center was the spherical Earth, containing the 4 elements: earth, water, air, and fire. Everything outside of the sphere of the Earth was made of a 5th element called the ether. This 5th element, or quinta essentia in Latin, is where we get the word quintessence. The sphere of the Earth was stationary, but it was surrounded by a set of transparent nested spheres which could rotate. The fixed stars were attached to the outermost sphere. The other celestial bodies were attached to the nested spheres inside the one for the fixed stars. Now, drawing 3D spheres is beyond my artistic abilities, so here the circles represent the path of the celestial objects that would be produced by the rotation of the spheres. Having all these spheres rotating around the Earth once a day, in a clockwise motion as seen from above the North Pole, would account for the diurnal motion of the Sun, Moon, planets, and stars, rising in the east and setting in the west. However, as we have seen, in addition to the diurnal motion, the Sun also slowly shifts to the east relative to the fixed stars. The Moon and planets also shift to the east each day at their own rates. This requires adding other spheres that move relative to the main spheres to account for these motions. Again, I'm just going to use circles to represent the resulting motion relative to the fixed stars. In this model, a year is the time it takes for the Sun, that's the big yellow one about 4 rings out from the Earth, to go around the Earth one time. The time it takes for the other inner planets as well as the Moon, so in other words, Mars, Venus, and Mercury, and the Moon, to go around the Earth one time are shown proportionally. The outer planets are not shown proportionally because that would take too long. They have really long years. Including the motion of the planets in this system introduces another complication. That is because the planets usually shift their positions in the sky to the east, but not always. As this animation shows, if we plot the location of a planet over time, we will see that occasionally it will stop shifting eastward and start shifting westward for a while before returning to the usual direction. This is known as retrograde motion. Supposedly, Aristotle's model, by using up to 55 nested spheres, could account for all the basic motions of the celestial objects, including retrograde motion, but only in a qualitative way. One couldn't use the model to make accurate predictions about planetary locations. Also, this model predicts that the Sun, Moon, and planets will always be the same distance away from the Earth. Thus, the model could not explain observations such as the varying apparent size of the Moon, which changes by as much as 11%. Other ancient astronomers, most notably Hipparchus and Claudius Ptolemy, were able to model planetary motion more precisely and accurately by using a concept called the epicycle. With an epicycle, the planet didn't orbit the Earth in a circular path, but instead followed a smaller circular path called an epicycle. The center of the epicycle is what moved around the Earth in a circular path called the deferent. We can use the Lego model to visualize this motion. I have removed the small Earth from the model because we are going to pretend that the big yellow one in the middle is the Earth for this demonstration. The small gray moon on the model will represent our planet in orbit on an epicycle. Notice that the planet, although it is always moving counterclockwise along its epicycle, appears to be moving relative to the Earth in the center, sometimes clockwise and sometimes counterclockwise. When we look at it from the side, this looks like shifting eastward over time, then westward, then eastward again. Keep in mind that the planets don't exhibit retrograde motion as often as this model would show it. For example, Mercury goes into retrograde most often, 3 or 4 times per year, while Mars goes into retrograde approximately every 26 months. Claudius Ptolemy, who lived from about 100 AD to 170 AD, wasn't the first to use epicycles and deferents. However, his model yielded more accurate predictions than previous geocentric systems. Ptolemy's system became the standard astronomical model for over 1,000 years. The name Ptolemy and geocentrism have become so closely associated with each other that the terms are sometimes used interchangeably. Next time, we will look at some objections to geocentrism, and we will see how a Catholic cleric named Copernicus revive the heliocentric model. Until then, look to the stars.